Exxon's looking at a project down near Houston where they're hoping to do 10 megatons of CO2. You need 110 megaton plants to make a billion.
Right.
Yet they're one of the larger emitters in the United States.
One of the leaders, I must say.
A lot of us are trying to address a gigaton problem with kiloton and megaton solutions. Even if we're completely successful, it's not going to move the needle. When humans are putting out 40 gigatons,
Well, joining me today is Dr. Brent Constantz, CEO of Blue Planet Systems, where they're transforming carbon emissions into building materials. Excited to dive into this story and their game-changing approach to climate tech. Brent, thank you so much for making the time to join us today. I'm excited to have you on our show. Where are you calling in from today?
Los Gatos, California, which is Blue Planet's headquarters.
Oh, awesome. How long have you guys been out of there?
About 12 years.
12 years. Oh, wonderful. Okay. Brent, I did see you guys' recent post about the first net zero concrete slab that you guys poured. Major milestone. Congratulations to you and your team.
Thanks.
Brent, can you tell me about your role at Blue Planet Systems? What does your day-to-day focus look like as CEO?
Well, we have two basic operations going here at headquarters. We're doing a lot of testing and characterization of our technology and our products, and then across the bay in Pittsburgh, California, about an hour away on the bay, we have a plant which has a few acres of waterfront where we can bring in large Panamax vessels, that carry 70,000 tons of material in and out. So it's sort of a dual function, both supervising a first-of-kind plant of a new technology that's scaled up, going commercial, as well as running a global R&D organization where we're working in a number of countries developing new projects.
It's terrific. When you say a number of countries, whereabouts?
We've applied for patents in a number of countries around the world, but in terms of active project development, there's several European countries where we're working with partners, but we have a partnership in Singapore, for example. Some work in South Korea, Australia, a little bit of discussion in China, work in Canada, and around the U.S.
Oh,
These are all sites where we would develop Blue Planet operations, capturing CO2 and producing limestone.
That's amazing. So truly a global enterprise.
Yeah.
Brent, you have a really unique background in biomineralization. How did that lead you to founding Blue Planet?
Well, when you look where the carbon is on Earth, when you talk to most people, they'll tell you that it's, CO2 in the atmosphere. It turns out that's the smallest reservoir of carbon. We divide the planet into 4 different spheres. There's the atmosphere, which is about a 80,000 foot thick layer of gas around the Earth. But there's also the whole biosphere, which is all the plants, animals, all the animal tissue, grain forests, plankton in the oceans. And then there's the hydrosphere, all the lakes, rivers, oceans, ice caps, water. And then there's the lithosphere, which is all the solid earth, right? And a lot of people don't realize, but only a very small part of the carbon on Earth is sitting in the atmosphere. It's about 800, what are called gigatons. A gigaton is a billion tons. There's about 800 gigatons of carbon in Earth's atmosphere. But if you go to the biosphere, there's about over 2,000 gigatons. compared to 800 in the atmosphere. So there's almost 3 times more carbon in the biosphere than the atmosphere. But when you go to the hydrosphere in the ocean, there's about 38,000 gigatons of carbon, compared to 2,000 in the biosphere and 800 in the atmosphere, which sounds like a lot. And that's as bicarbonate ion mainly in the oceans. But in the lithosphere, as rock, there's over 100 million gigatons.
Wow.
And it's almost all limestone.
Right.
So it's like the White Cliffs of Dover, the Great Barrier Reef. In the U.S., we know about the Austin Chalk, limestone in Indiana. That's all calcium carbonate, which, is what most, clam shells are made out of, and oyster shells and lobster shells, and almost all that limestone is the skeletons of ancient marine organisms.
Yeah, that's right.
Like the Great Barrier Reef, it's mostly coral skeleton. The White Cliffs of Dover, it's what are called calcareous nanoplankton, but they're little small plants in the ocean that are responsible for a lot of the oxygen, making oxygen, and the primary carbon fixation in the planet. So biomineralization is the study of how organisms form minerals, like our teeth and our bones and coral skeleton and stuff like that. But as you can see from those numbers, almost all the carbon on the planet is in limestone. And limestone is the result of biomineralization.
Right.
So by studying biomineralization, we can understand how carbon gets fixed and mineralized and taken out of the atmosphere where it causes global warming.
Honestly, in my mind, I had no idea that the relation, from carbon found in the ground to what you'd find, in our atmosphere. So that's absolutely fascinating. Thanks for sharing that. But also similar, related to that question, I know you guys at Blue Planet Systems have set a very bold vision to mineralize 1 billion tons of CO₂. So what does that vision mean practically, and why is that important, Brent?
Well, the reason it's important is having to do with the scale. There's dozens or probably hundreds, even thousands of efforts today aiming to reduce their carbon footprint or reduce the carbon intensity. We want to burn less coal, go renewable, all that stuff. And but nobody's really gone through the numbers like I just did for you about where all the carbon is and how much of it there is.
Right.
And there's what we call kiloton efforts, which is like hundreds of tons, or thousands, a few thousand tons CO₂. And humans put out 40 gigatons of CO₂ a year. So
Wow.
something that does thousands isn't even going to show up, right? 1,000 means 3 zeros on the end. And some of the biggest projects are what are called megaton level, and that's millions of tons. So now you have 6 zeros instead of 3.
Right.
So it's millions of tons. Well, there's a 1,000 millions in a billion. So you need 1,000 1 megaton plants absorbing CO₂ to get 1 gigaton of CO₂. And if you take all these efforts that are announced as major carbon sequestration efforts, they're unlikely to even get to a megaton,
Right.
let alone a
That's a
kiloton.
that's a lot
And
of weight.
what's going on out there right now is there are middlemen trying to monetize carbon, and they're outselling tens to hundreds of carbon credits, as though that's going to have some significant effect. If
Right.
those credits do represent mitigation of carbon, which in a lot of cases they don't anyway. But so what's significant about billions of tons or 1 gigaton is that's the order of magnitude that you have to be working to be doing anything that really makes any difference. Humans put out 40 gigatons of CO2, like I was saying.
Right.
And, the only place where you're going to get that amount of carbon is actually in rock, just like on Earth. Over 99% of the carbon on Earth is in rock, in limestone. Yeah, but what's important about limestone is, other than water, it's the largest commodity on the planet. So there's 55 gigatons of rock mined and moved every year for construction. And we know in construction, what's the most common building material? Concrete.
Concrete, sorry. That's eye-opening when you speak in that scale and those numbers.
Concrete, the most common building material, is about 80% what's called aggregate. Fine aggregate is sand, and coarse aggregate is rock or gravel. And most of that is limestone, because limestone is easier to quarry. It chemically bonds well in the concrete. And so the point is that if you really want to sequester a lot of carbon or capture carbon and get it out of the atmosphere, there's always the question, what are you going to do with it?
Right.
And just to put it in perspective, Exxon's looking at a project down near Houston where they're hoping to do 10 megatons of CO2. Okay. Now you need 100 10 megaton plants to make a billion, right?
Right.
So this one project, the biggest project they're doing, is 10 megatons. Yet they're one of the larger emitters in the United States.
And I was going to say that they're one of the leaders, I must say. I'd assume, right?
Yeah. So, the point is, we're trying to. A lot of us are trying to address a gigaton problem with kiloton and megaton solutions.
Right.
And even if we're completely successful, it's not going to move the needle, because when humans are putting out 40 gigatons, you need something that has that capacity. And rock, that 55 gigatons of mined rock, is about of the same order of magnitude as the 40 gigatons of CO2 that humans put out. And, the rock itself, most of it's limestone. And limestone is calcium carbonate. And there's one CO2 in every mole of limestone. So if I have a ton of limestone, I've got 440 kilograms of carbon dioxide trapped inside that limestone in the crystalline state. So by making CO2 into limestone and then using the limestone in the construction as concrete, you've got an already made reservoir and market for the CO2.
Absolutely.
And we're going to use concrete. We're not ever going to stop using concrete. I can guarantee you.
Right. That's terrific. How to make such benefit out of a byproduct from another uh, product or industry, right? So that's absolutely terrific. So Brett, for people unfamiliar with this space, how exactly does your guys' technology capture and mineralize the CO2 into building materials and concrete?
Yeah. So there's a concept in design and these days called biomimetics, mimicking biological systems. And you see a lot of this in heating and cooling of buildings. There's been a lot of bio-inspired designs from nature, how to do things like that. And in terms of forming limestone, the inspiration actually comes from biomineralization, from observing how all the marine organisms that make limestone, that make these calcium carbonate shells that turn into limestone, how they do it. And it turns out that, in chemistry, some chemical reactions use energy, some of them don't. And the formation of the carbonate for the calcium carbonate in the skeletons of these marine organisms doesn't, it's what we call a downhill pathway. It's a spontaneous reaction that occurs. And it's distinguished from anyone else trying to capture and manipulate CO2, like Exxon, for example. They take the CO2 as a gas and then purify it, which takes a lot of energy. And then they have to keep it compressed in a liquid form to handle it, which also uses a lot of energy. What happens at our plant is we take the raw flue gas from an adjoining power plant and we just convert it into carbonate. And it's a downhill spontaneous reaction, just like it is in nature. And it doesn't use a lot of energy. So just as a way to manage carbon, capture carbon and manage it, because we're taking our inspiration from nature, we have the lowest energy method of doing it, which is a big deal because a lot of these methods produce more CO2 than they capture. They use so much energy.
Counterintuitive, right? Yeah.
Yeah. And so that's a key part of our process is the spontaneous absorption and conversion of carbon dioxide. We like to say we only touch it once. So we're not going through a lot of processing steps and all that. We just convert the CO2 at any concentration to carbonate and make calcium carbonate and make that into limestone.
So you'd say it's a pretty high efficient process.
Yeah, it's by far the lowest energy method to capture carbon from CO2 and contain it. Yeah.
That's awesome. I love that, Brent. So Brent, tell me, from your vantage point, what kind of trends are shaping the future of sustainable construction?
Well, I'll give you an example. Um, when we make concrete out of our limestone, it's made out of 40% CO2. So, as you're probably aware, there are companies like Microsoft, for example, that have set goals to be carbon neutral by 2029, 2030, that kind of thing. So there's a big push to have a low carbon building. And, for example, we were invited by one of the social media companies to meet with their architects and talk about the carbon footprint of a large campus they're building. And between the concrete and the steel and the glazing, there's no way they could meet their goal of being carbon neutral. So we started having discussions about, well, could we take the concrete, which is carbon negative, because the Blue Planet concrete is made with rock, limestone as aggregate that's got CO2 in it, and it makes the concrete carbon negative. And the question was, how much concrete are we using in the project, and how carbon negative could we make the concrete to offset the carbon footprint of the steel and the glazing? Because steel has a huge carbon footprint, and so does glass. And usually concrete does, but our concrete is actually carbon negative because we're sequestering CO2 in it.
Right.
Which offsets the carbon footprint from the steel and the glass, and making the whole thing carbon neutral or even carbon negative. And the way it affects things is, well, for example, I was at a similar meeting at another Silicon Valley company, and the structural engineer came in and said, hey, we just cut the amount of concrete in this building in half. And I said, well, why did you do that? He said, well, I'm trying to lower its carbon footprint. And I said, well, wait a second, this is carbon negative concrete. So you actually want to double the amount of concrete you use. Because the more concrete you use, the more carbon you're sequestering. And that's going to be a real trend as more and more carbon negative materials become available. I mean, the classic carbon negative material is wood, right? Because
Right.
when trees grow, they capture CO2 and it goes into the cellulose and into the wood. But since concrete is such a common material, switching it from a carbon intense material to a carbon negative material is going to affect all construction in a
Right.
big way. And if you talk to people in the construction industry these days, you'll see almost a significant amount of what they're doing is driven by trying to get to a lower carbon building. Whether it's building materials or the processes around making buildings.
Right.
And the whole idea of, gee, we're going to use more concrete here to lower the carbon footprint of the building is counterintuitive. When you use more concrete, though, you can do things that you can't do with normal construction. Like, say go to Europe and look at the buildings that were constructed before steel came along, and look at the ones after steel. The ones before steel that didn't have, the tensile strength of steel, like in rebar and, beams and things like that, are dominated by either stone or actually concrete because it's very strong in compression.
Right.
It doesn't need a lot of tensile forces, to hold up because you've got a big, like a pyramid, big solid.
Right. Foundations.
Yeah, with a keystone. And, but if they have the possibility of using more concrete, they'll use less steel. But you're also designing the whole building differently, right? You're making thicker walls, doing things differently, which affect the heating and cooling and number of aspects. So I think that's, from my perspective, one of the biggest trends is the use of carbon negative materials.
That's immensely exciting. That's got to get you guys pretty wound, pretty excited on your guys' end as well, knowing that's coming down the pipeline.
Yeah, well, you have to, um, broadly look at the goal of decarbonizing the built environment. and say, okay, what's possible? And
Absolutely.
the way it actually gets enacted often, maybe it isn't taking it as far as it needs to go. They're like, I think the LEED 5.0 is got up to 10 points for various aspects of decarbonizing concrete, but it's not quantitated. So it could just be fairy dust, and they call it green. But there's a new certification system called Carbon Star, and it's patterned after Energy Star, but it describes the carbon footprint of a cubic yard of concrete. In fact, San Francisco Airport uses it to specify their concrete. But you need that kind of rigor to really make a difference. Otherwise, you just get a sort of a greenwashing, that doesn't really make any difference.
That's totally eye-opening and jaw-dropping. It really is. So, Brent, thank you again for your time today. This was truly a masterclass in innovation and climate tech leadership. I'll follow up with a summary, and I look forward to seeing where you guys with Blue Planet Systems go from here and what you guys are up to next.